Okay, when we talk about load tracing, we're starting from the top and working our way down always. So load tracing is a systematic process of determining the loads and support reactions of individual members. So we will go from just the base, just the decking, planks, whatever the case may be, to the beams, to the joists, to the girders, to the columns, to the soil. Okay, that's kind of how we'll be going in this class. Do we need to make this area loading into a distributed load? Then it goes to a concentrated load. We need to be able to identify what each one of those is doing and the loading that it's creating for the next member. So we do this by using free body diagrams and the equations of equilibrium, and we can find how much load each member is carrying. So that is ultimately the goal of load tracing, is figuring out, okay, for this beam, how much is that? How much is the loading on that? Is it rated for that? Is it under capacity? Do we need to do something else here in order for it to be rerouted in order for that load to be lessened? So the process starts again with the uppermost, tracing all the way down layer by layer until we get a ground reaction. Okay. So again, like I said, area loads from roof to floor becoming distributed loads on trusses and joints. So trusses and joints reaction become point loads on the studs below. So basically what that's saying is we're going to start off with the uppermost, and we're saying that this got hit with a lot of snow, about 10 pounds per square foot or something like that. We need to take that distributed load, so it's little tiny arrows all over this, right? And where is that supposed to go next? Where is that snow load supposed to be dissipated to? Yes, the members itself can, but it's then going to these joists here, this pitched framework. So all of this area loads needs to be divided between 1, 2, 3, 4, 5 different joists, and each one of those are going to get its own little distributed load on top of there based off of what it was holding from that area load. So every joist is going to be given a little portion of that, and then it moves on to the next thing. Okay, we got that. Then we're going to go to the bearing wall, and those joists are evenly distributed over that bearing wall. So that's what we got. It'll move straight through. We need some arching around this window here. So the ones on the outside might be a little bit more, but still uniform. And then we're going from joist to bearing wall to ground again. So understanding that route, understanding pounds per linear foot. So getting from area load to distributed load we will talk about, but that is ultimately the goal. How do we make something from a distributed load and carry that throughout? Okay, when we're talking about the framing design criteria, structural framing can contribute significantly to the architecture of the building. So they're always thinking about efficiency, economy. When something doesn't quite make sense to us, it's usually because, is this building just meant to park cars under, or is it meant to stand out as art, as an architectural design piece? And so that comes with different material types, what kind of labor and skill those laborers have, and efficiency and economy. Sometimes you just don't have the money to make the garage car look really appealing and cool and new, and it doesn't need it. So different material types. Mechanical and electrical system requirements. What is this building? Again, is it just a storage facility? Is it meant to throw wedding parties? Whatever the case may be, system requirements, does it have all the components required for that? And then designing around openings as well. So staircases to attics to windows. Are we able to move those forces around and still get the loading required done safely? Okay, so these are a couple different types of wall systems that we could have. This one's called a uniform slab. So as we can see, all of this is just a concrete slab. And what that's creating is a uniform distributed load over our bearing wall here, our masonry wall, and then that creates another just completely distributed load down to the footing, and then that down to the soil. So that's just nice uniform distributed loads from top to bottom. That's the same thing if it's joists, but they're spaced out evenly. They have the same distance in between all of them. It is going to create a uniform load distribution. They're going to go down in different ways. This one would be more straight down, but this one's going from side to side. But the way that those angles work out, everything's coming down nice and uniform by the time it hits the footing, which is not the case if there are wide spaces in between the beams here. So when that's the case, and there's just a couple, usually those forces, they're designing them to come off 45 to 60 degrees. Okay, so when it's hitting there, as you can see, that is not a uniform distribution as it's hitting the footing. It's more linear in shape, coming maybe at 60, 45 degree angles, whatever the case may be, however they designed it, not uniform for the footing, all because the loading is going to two beams that are not equally spaced out on the wall. Okay, there may be some gap differences between there and there. Something to look out for. Concentrated loads. Okay, same thing for arches and openings. When we have that case, we're designing around. How is that load moving throughout? As you can see, underneath the window and the opening, it can't hold anything in compression. There would be glass there, and so it's not going to be holding anything to the concrete footing. Same thing for here, any kind of window, base, that design, uniform loading on top, angling to get around to get back to the concrete footing without damaging that opening or utilizing it as a structural piece. Okay, roof and floor plans, from simple to complicated based off of the structure. This is a one level, so it's just precast concrete, could be planks, decking, whatever the case may be, and it's going and sitting directly on bearing walls, obviously the most economical way to do it. Second way would be a double level framing, so we'd have the decking, plank sheathing, whatever the case may be. We're going to the joist and then to the bearing walls, and then our third would be decking, sheathing, joist, with beams and girders, and then down to our columns. So again, just being able to add to the complexity because of what the design requirements are. We may get to the point of having to go from decking to joists to girders to columns. That is hopefully the goal in this class, to be able to do that. And then the last one I want to talk about was foundational system load paths. So these are column footings. How are we getting completely to the soil? What does that last step look like? One is spread footing, so vertical loads. This is simple and economical. This is for moderate to high soil bearing capacities though. So this is definitely based off of the environment that whatever the structure is being built in. Can the soil, what is the soil capacity? Can we go moderate to high loads, vertical loads, and be fine, or would we experience some sinking? Those can be circular, square, whatever the case may be. And then next would be wall footing. So these are the most common. Uniform wall, bearing wall through continuous foundation wall. So again, distributed loads, continuous. When you get to the soil here, it should be continuous underneath the concrete footing, unlike mat or raft foundation, where this is for low load capacity soil bearing, and that is going to take place underneath the entire structure. So that mat takes place underneath the entire building, and it's distributing the entire load out through the entire structure. Go to the next one. Okay, so one of the hardest concepts to begin with for load tracing is getting the tributary dimensions. So the loads are uniformly distributed over an area or roof or floor, are assigned to individual members, rafters, joists, beams, or girders, based on the concept of tributary area. So we are always going to start off, the problem is always going to start off with, these are the live loads and the dead loads that are acting on the first layer of the structure. Okay, so in this case, it's saying that all of this is the same loading, that all of that is uniform. All of these little arrows are acting. We get it? We get it? There's tons of little arrows all over. All of them are acting on the entire length of this, but when we get down to the deck, from the deck to the beams, each one of those beams has to take a little portion of that decking, okay? What is that portion is what the tributary width is. Okay, so when we look at A, what it's going to be is half the distance between one beam to the next. So it always goes half and half, especially if they're equally spaced, it's going to go half and half. So for A to B, because it's only 4 feet between the two, the tributary width of A is going to be 2 feet. So that is the little width that A is responsible for, that the beam A is responsible for is 2, and it is spanning over 6 feet, okay? So A is also 6 feet, but it only has 2. B, obviously, it's more in the middle, doesn't have the side support, and so it has not only between A and B, but also B and C. So now that is B's, and so is that. And that is why for B and for C, it's the same thing for C, and between B and C, and in between C and D, both of those, the beam at B and the beam at C, both have a tributary width of 4 feet. Okay, so B and C would have the higher loading for this decking because they're in the middle, because they're in charge of more of the load. Okay, so what we want to do here, what we should be able to see is making a really wide, it's 3-dimensional, okay, this is like our first 3-dimensional look, but what we're always trying to do is get back into 2D, get it back onto an X and Y plane. So how are we going to squish this loading to being flat again over these beams? Is overall the concept of load tracing. So tributary area is going to be the span times the tributary width. So A's tributary area is going to be it's 6 feet and it's 2 feet wide. And then for B and C, it's going to be the same span length of 6 feet, but each of those are going to be 4 feet wide. Okay, so a little bit difference, double for B and C, just because of the tributary width